Good evening, everyone, and welcome to the talk. I must say, I've never in my life seen so many people come free willingly on a Tuesday night to a physics lecture. But I think there's a big reason for it. So I really want to give a special welcome to Professor Ian Hutchinson. He's a professor of nuclear science and engineering at MIT, and we're so lucky to have you here. So a big round of applause for him. Yeah, so the topic of today is, could we use the unlimited power of the stars here on Earth? Just to inform you guys, there's a Q&A session at the end. You can either ask a question from the floor, or if you want, you can scan this code, and then while he speaks, if you think of a question, pop it in the QR code, and we will address these questions later. And now I want to give over to Professor Leuthold. He's the department head of the electrical engineering department at ETH, and he's going to introduce Professor Hutchinson.
Thank you. Good evening, everybody. I have the privilege to stand here also as a member of the Professors or Lecturers Forum. This is a group of professors that love both science, but also discussions about God and the world. Now, this evening is about the Templeton Lecture. The Templeton Lecture goes back to John Templeton, who in 1996 founded a fund to support lectures that are dedicated both to science, but also are open for philosophical discussions. And sure, we have something which is of societal relevance tonight, and we have a very interesting guest here. Professor Ian Hutchinson. He is professor of nuclear science and engineering at the MIT. MIT, Massachusetts Institute of Technology, it's according to US World Ranking, the #1 university. And just as a reminder, ETH is #7.
Okay.
Good. Hutchinson, he is of course a carrier. He has received his bachelor in Cambridge University in 1972. He got a PhD from the Australian National University in 1976. And he was subsequently one of the first in the West that worked with these tokamaks, a word you were gonna see many times probably tonight. These are these little toys where you try to create plasma so hot that you can generate energy like the sun is doing every day. In 1983, he became a faculty of MIT, and between 2003 and 2009, he was the head of the department. He has a distinguished career in plasma physics. He holds this distinction to have invented how to really measure plasma in flow. He has made analytical contributions and contributed a lot of theories. And if you look more closely into his CV, then you find he wrote one of the standard textbooks in plasma physics, Principles of Plasma Diagnostics, a book written in 2002. And I tell you something, this seems to be one of the books that actually get read, according to the many citations I've seen. Besides, there is a member of editorial board, a fellow of the Plasma Physics Society, a recipient of many prizes, and most importantly, when he has time left, he seems to do some computer programming. So if you have ever wondered how to bring math equations in the web, he is the author of the computergram Tech to HTML, a program that many people use for the conversion of equations. And besides that, he has many other interests because he has written several books on the relationship between science and Christian faith and faith in general. I think he's one of the people that will be, at the end of this lecture, an interesting partner to discuss both sides, but also other questions. Ian Hutchinson, please.
Thank you. Thank you. Here's the true title of my talk. And my plan for this talk is to tell you about fusion, yes, but also to speak more personally about my career in fusion research and, in a small way, how my science relates to my spiritual commitments. Nuclear reactions are what we start with in this business, and fusion is a type of nuclear reaction in which light atomic nuclei are fused together to get heavier ones. If you could zoom down to the scale of 1/4,000,000th of a meter, then this might be a useful cartoon representation of a fusion reaction. Two isotopes of hydrogen, hydrogen has one proton in its nucleus, and either 1, 2, or 0, if it's purely hydrogen, protons, those are the blue things. If you bring two of those hydrogen nuclei together, they can react by nuclear reactions and give rise to a heavier nucleus, helium in this case, and maybe neutrons. And fusion is such that it releases energy because the two products are lighter than the two hydrogen nuclei we had in the first place. And because of that fact, large amounts of kinetic energy are released because of Einstein's relationship, E equals mc squared. The other type, by the way, of nuclear reaction that we have is called fission. That is breaking a heavy nucleus, like uranium, into two lighter nuclei, and that also yields energy. It moves up this binding energy curve in such a way that kinetic energy is released. And fission is what we currently have for the reactors that power much of our electric grid today. Now, fusion nuclei, the things which we're reacting together, we have two positively charged nuclei, and they repel one another. And to overcome that repulsion and get them close enough for fusion reactions to take place requires very high kinetic energy. We have to crash them together. And that means high temperature. And we know by calculation and by actually measurement of these fusion reactions that the rate of those can be discovered, and you can plot it as a function of the temperature of the reactants, and the rate is the number of reactions per unit time. And the shape of these reaction rates is such that for any relatively low temperatures, less than maybe 10 million degrees Kelvin, the reaction rate becomes vanishingly exponentially small. So for fusion to take place on the Earth, at any rate, we need an optimal temperature of about 100 million degrees Kelvin. And for any temperature that's of order 1,000 Kelvin or more, all matter is in the ionized plasma state, in which the electrons are stripped away from the nuclei, and they move around separately, and therefore they conduct electricity. They have very different types of phenomena than gases made up of neutral atoms. Actually, plasmas are everywhere in the universe. Most of the matter in the universe is hot plasma, nebulae, galaxies, and stars particularly. And almost all radiation is produced by plasma processes, and that's how astronomy detects the universe. A planet like the Earth, on the other hand, is cold, so we're not so familiar on Earth with plasmas. But even so, there are plasmas that occur naturally, for example, auroras or lightning. And actually, we on Earth can produce plasmas by intelligent activity, for example, a cutting torch, or in particular, materials processing, which is what underlies the manufacture of most semiconductors these days. Well, as we've heard, I was an undergraduate at Cambridge University in the 1970s, and I actually became a Christian in my second year. But as my degree completion approached, I became interested to do further study of the physics of the plasma state. I had an invitation to stay at Cambridge to do doctoral studies there, but I felt a call instead to go to Australia. And when I won a fellowship to go to the Australian National University, that seemed to confirm the idea that this idea was part of God's plan for me. And I was thinking that perhaps I would work on astrophysical plasmas like those that I was just showing you. But it turned out instead that at the Australian National University, there was a plasma confinement experiment of a type that had just been discovered to have very favorable performance properties for fusion. So when I arrived there in Australia, I had an amazing opportunity to do important experiments in fusion research. Now, a fusion reactor needs to contain very hot reacting plasma using an immaterial force. Nature's fusion reactors, the stars, are held together by gravity. Their center, where the fusion reactions are taking place, is much hotter, it's millions of degrees Kelvin, than their surface, which is more like thousands of degrees Kelvin. And the heat is conducted from the center of the star towards the edges, and then at the edge of the star, it's converted into radiation, and it's radiated away, fortunately for us, keeping the Earth, a planet nearby the sun, warm, okay? But gravity is a very weak force, and as a result, it becomes strong enough to confine plasmas for fusion only in very large objects, basically stars. It's interesting that the first ideas about fusion reactions were hypotheses put forward, in this case by Arthur Stanley Eddington, in 1920. In 1920, nobody knew anything about nuclear reactions at all. But they knew that the Earth was old and that there needed to be a mechanism for keeping the sun hot. And here is what Eddington said about this. A star is drawing on some vast reservoir of energy by means unknown to us. This reservoir can scarcely be other than the subatomic energy, nuclear energy, which it is known exists abundantly in all matter. We sometimes dream that man will one day learn how to release it and use it for his service. And it is that dream that humanity has been chasing or exploring since the 1950s, actually. That dream is what I'm talking about. Actually, just to finish the story about Eddington, the reason why he was able to make this prediction in 1920 is that it had just been discovered that the constituents that go to make up helium are actually heavier than the helium nucleus itself. And they knew Einstein's relationship equals mc squared, but they didn't know how it could possibly take place. Okay, well, to do fusion on the human scale, on the terrestrial scale, you need a stronger force than gravity because you have to do it in a smaller size. And the most useful force for that is the force of a magnetic field. What a magnetic field does is to cause the free plasma electrons and nuclei to spiral around the field lines so that they can move relatively freely along the field lines, but they can't move across the field lines. And that's how magnetic confinement of plasma works. An alternative approach that is still being pursued is to make reactions happen so quickly that they're all completed by the time that the hot plasma flies apart. In other words, the plasma is held together only by its inertia, and that's called inertial confinement. It's actually the type of event that happens in a hydrogen bomb. But so basically, the plasma isn't really confined per se, but it's basically all over before the plasma can fly apart. But these two approaches to trying to produce useful energy on Earth lead to conceptions of the systems that would give rise to useful energy that look rather different. In the case of magnetic confinement, we would need to have a fairly big device, big electromagnets that are generating strong magnetic fields that confine the plasma, whereas in the case of inertial confinement, we're talking about actually very small plasmas, taking a pellet of this millimeter size and compressing it even further, and essentially setting off miniature hydrogen explosions repetitively. Of course, the objective then would be to gather the energy up and drive some kind of electric generator and put the electricity on the grid, and that's the vision of fusion energy. Net power production from virtually any system basically needs us to reach ignition. What is ignition? If you think about chemical burning, let's say the burning of wood, if you hold a flame up to wood, eventually it's going to smoke and start to burn. The wood itself is going to start to burn. The question is, what happens when you take the flame away? Does the wood keep burning? Does the fire burn up? Or does it just fizzle out? And the answer to the question, will it or won't it keep burning, is it'll only keep burning if it's losing energy from the fire faster than it's generating its own energy by the chemical reactions that are taking place. And so it's governed by what we call an energy confinement time. Well, nuclear fusion has the same principle. The only difference is we're talking about nuclear reactions rather than chemical reactions. So there is, in principle, if you're trying to confine a plasma, there is some time scale on which the energy is going to gradually leak out of the plasma, and we call that the confinement time, and it's denoted by the Greek letter tau. That's how long the plasma would remain hot if we took away all the heat. And one can be shown that if we're thinking about deuterium-tritium fusion, the degree of confinement that we have to attain in order to reach that point of ignition, where we're losing heat less quickly than we're reacting to produce it, is when the pressure of the plasma and multiplied by the confinement time has a value of about 20 atmosphere seconds or bar seconds. So, for example, what that means is if we have 1 second of confinement time for the plasma, then we would have to have a pressure of 20 atmospheres, 20 times the pressure of air in this room. On the other hand, if we have a confinement time that's about a nanosecond or less, then we need 20 billion bars of pressure. And that's the characteristic more of inertial fusion. So these two things are sort of representative of the kind of target we're shooting for in magnetic and inertial confinement. Now, since 1950s, when fusion research began, there have been literally hundreds and hundreds of different configurations of magnetic confinement that have been built and studied. And these photos are just a tiny fraction of to give you the idea of what these things vaguely look like. And all of this, of course, has been trying to find out the best way to confine a plasma for the purposes of fusion. And the remarkable thing about almost all of the explorative experiments that have been done is that almost none of them give anything like good enough confinement to have a hope of making fusion energy. So if you read in the newspaper these days, someone claims to have some new brilliant idea for how to make fusion work, you should immediately be skeptical, because quite likely this idea was had 50 or 60 years ago, was explored and found to be unworkable. What we now know is that in order to make magnetic confinement work well, by far the most important feature is that the field lines must have no end. This should be no surprise if you understand that magnetic confinement mostly confines across the field and not along the field, so it's not a big surprise. So if you follow field lines, this is a representation of the way you get a confinement configuration that the field lines have no ends, is you basically make them go round and around. And in America, we would call this generic shape a donut, but actually, technically, it's a torus, okay? So it's a toroidal confinement device. There's one other aspect of this that's very important. It turns out that in addition to the magnetic field lines going the long way around the torus, they must also have a twist so that as they're going the long way around the torus, they're also going the short way around the torus. That's at a noticeable amount. And if you look carefully at that picture, you can see that, for example, the green line is going around the torus with a twist. During my 3 years of doctoral studies in Australia, I learned Hebrew. I trained as a Methodist preacher. I married my wife, who was an IFES student leader at the time. This is we just celebrated our 49th wedding anniversary. I finished my experimental doctoral research on what we used to call the first tokamak in the free world. And then I went on to jobs as a research scientist at MIT and in the UK. And I returned, as you've heard, to MIT in 1983 on the faculty, and so I just completed my 40th year. And in 1987, I became the director of tokamak research there, leading the construction of a new experiment. Now, what do tokamaks actually look like? Here are a couple of photographs. On the left-hand side is a photograph of JET, the Joint European Torus, and it was sited near Oxford. And what we're looking at is the inside of the vacuum vessel with a wide-angle camera. And this chap in white is working inside the vacuum vessel. He's there to give you an impression of the size of this device. So this device, built in the 1980s, was pretty darn big. Of course, he better make sure that he's not there when we're actually putting a plasma in there, because he would be vaporized in less than a second. This is a photograph, by contrast, of the newest tokamak to come into operation, which is built in Japan. It's called JT60. It's about the same size as JET, but its claim to fame is that it uses superconducting magnets, which magnetically confined fusion will have to do in the long term in order to keep the magnets going without having to expend a lot of energy in order to drive the currents in the electromagnets. You can see the size of the co-workers just barely in this picture, but the purpose of this picture is to give you the impression that this is an enormously complicated device, and this was in the latter stages of its construction. The tokamak that we built at MIT was a lot smaller than JET. So there's a person inside it here, but you can see that person's pretty cramped. Actually, I and my colleagues spent many happy hours crawling around inside that. It was like we were like spelunkers inside of that vacuum vessel and installing things inside of it. And that shows you that this was a much smaller device than JET. This is a photograph of the actual plasma, basically with the same kind of perspective, of the actual plasma in operation inside of our tokamak. What you notice is that it's actually only the edges of the plasma that are being seen in visible light. And the reason for that is this plasma, like other tokamaks, is so hot that the center of the plasma only radiates in the extreme ultraviolet and X-ray region, and it's only the very much colder edges, actually just like the sun, very much colder edges that radiate visible radiation. These lines, yellow lines drawn over the photograph on this side, are to give you an impression of how the magnetic field lines wander as they go around the long way. They trace out surfaces that are nested, and the center is, of course, in the middle there, and the energy flow is essentially from the middle outwards. CMOD's claim to fame is that it had extremely high magnetic field, and that enabled it to contain very high pressures. And yet it achieved plasma performance that, as I'll show you a little bit later, was not that much worse than the very much bigger tokamaks that I've shown you. In fact, CMOD still holds the world record for confined plasma pressure. I'm often asked about the relationship between my science and my Christian faith. And the question sometimes supposes that there's a contradiction between them. There are in any person's life, puzzles that you have to work out about your different commitments, whatever they are too. But I've never felt that science and Christianity are contradictory. And by the way, nor have many of the greatest scientists of history. But one way in which I feel my faith has actually helped me to be a better scientist is that scientific leadership calls for effective personal interactions with people in one's team. And whatever personal, interpersonal skills I have were greatly helped by my Christian understanding of the human condition and by my activities of shared Bible study and prayer and these kinds of things. I led a terrific team of scientists, engineers, students, and technicians. It was a privilege that I very much appreciate, and I want to acknowledge them all in this photograph, which is actually a picture of us sitting on top of the tokamak that's under construction at this particular time. And I want to thank God for them. It was a wonderful experience. Well, I talked about how we confine plasma and try to keep it hot. The question is, how do we get it hot in the first place? How do we actually get those first fusion temperatures? Actually, there are several different methods. In a tokamak, we pass a big current the long way around the torus. Actually, it can be several millions of amps, and that is then operates really rather like a monstrous electric fire, bar fire, and so it puts a lot of heat into the plasma. And that heat is enough to get the temperature up to maybe 10 million degrees, but that's not really quite hot enough. And so we actually need other methods to get it the last little bit to ignition temperatures, optimal ignition temperatures. And one way is to fire in extremely energetic neutrals, which are able to penetrate the plasma and deposit their energy in them. And if you need an analogy to think about, it's like putting, a flamethrower on the fire. The only difference is flames are only, 1,000 or a couple of thousand degrees, whereas the energies of these particles are, more than 100 million degrees. The other way that we use is to use various types of electromagnetic waves and microwaves. These are, by analogy, very like a microwave oven. You put your food in the microwave oven, you turn on the magnetron, there's lots of microwaves, they're absorbed by the food, it heats it up. Well, if microwaves are absorbed by the plasma, it's going to heat them up too. Of course, we have a lot more power involved in these fusion devices than in a microwave oven, but it's a good analogy. And these techniques of heating the plasma have been proven over many decades of experiment to work quite well. They're based on existing technology, but of course, the energies, powers, and so forth that are involved in heating a plasma are much greater than people are used to for most of these techniques. And one way to illustrate this is a design that was planned some time ago to inject neutral heating into ITER. I'm going to talk about ITER later. This is the man next to it. And so you can see that the size of this injector is absolutely enormous in scale. And that's one of the challenges of fusion energy to bring us up to these very high temperatures. Another thing you might have been thinking about is, well, okay, how do you measure what the temperatures are in a plasma that's 100 million degrees hot? And the answer is with great difficulty sometimes, but you have to depend upon the physical phenomena that are going on at those incredibly high temperatures. And there's a whole variety of methods that we can use to measure plasmas. In some cases, the plasma is cold enough right at the edge that we can poke physical objects into it and do direct sensing of what the temperatures and densities are. But if you need to measure what's going on in the center of the plasma, you need some non-contact way. And one example of a method is to shoot a laser beam through and look at the scattering of the laser light, which then tells you what the density and temperature is. Or another way is not necessarily to send radiation into the plasma, but just to depend on the plasma's own radiation. These are, for example, X-rays emitted from our tokamak, where we've taken a spectrum of those X-ray emission lines, and the width of those emission lines tells us about the ion temperature of the plasma. Now, I've talked a lot about tokamaks. There's another type of magnetic confinement device, and they're called stellarators. The question is, how do you put the twist into your magnetic field line that I've talked about that we need? And in a tokamak, it comes from putting the current through the plasma. In a stellarator, instead, what you do is you twist the coils that you are going to use to generate the magnetic field. And these are a couple of examples of actual designed and built and operated stellarators, and they are a comparable way of approaching magnetic confinement. Actually, stellarators in the early days of fusion research had very poor performance and were largely abandoned by all but the most faithful of their practitioners. Actually, what happened was our ability to calculate how those magnetic coils should be twisted to give optimal confinement was gradually improved often by computer calculations. And so as that theoretical and computational ability improved, the confinement configurations improved, and it gradually appeared that stellarators might well have confinement nearly as good as tokamaks. And there's been great progress from the 1990 era onwards, and large superconducting stellarators have now been operated in Germany, this one, and in Japan, which one I'm not illustrating here. Well, okay, how are we doing in terms of performance? One way to plot this is this figure on the right. First of all, where do we need to get to? We need to get to ignition, or just below it, which is where we've really got a burning plasma. And when we started magnetic confinement research, the place we were was all off this graph, okay? These axes are logarithmic axes, so there's a factor of 10 increase in temperature or increase in confinement product pressure times confinement time as you go up through the major divisions of this plot. The points on the plot are experimental achievements of parametric achievements. The best tokamak in the 1960s was a tokamak called T3, and that was in Soviet Russia. And when that result was found, it was so much better than all these terrible results down here that everyone realized tokamaks are really a neat way to go, and they all started building them all around the world, America, France, and the UK, and lots of other places. And very rapidly, the confinement improved as we learned how to do this better, and also we learned how to heat the plasma, and so the green points go on and up, and eventually we reached a situation where JET, the tokamak I just showed you, and a comparable sized device called TFTR in America, were enabled to operate in deuterium and tritium. So they actually did fusion reactions in large amounts and they are the DT tokamaks, and they were at a line, that dashed line, which is not quite where we need to go, but it's a milestone on the way, which is called break even, which is when the fusion energy out equals the heating power in. We need to go further than that, but it's a nice milestone on the way. There are 3 points I've put on this plot also of stellarators, and you can see that much more recently, 2002 up to 2017, stellarators have also achieved confinement that is comparable to tokamaks, although in somewhat larger devices. You might have heard in the last few years, last two or three years, about laser fusion, and the achievements in that purple point at the top, labeled 2023, are what has been achieved by the NIF experiment at the Lawrence Livermore lab in California. But that's, of course, in a very different regime. It's something sub-nanosecond times, and it's not magnetic confinement. I won't dwell on the fact that JET and TFTR have substantially liberated fusion power. They were not to quite where we needed to go. But based on the results of the 1970s, we knew pretty well what is needed for this final step to a burning plasma. And eventually, in the 2000s, the governments of several nations agreed to build a scientific demonstration project called ITER that is sited in the south of France. And this is, a construction diagram of ITER. And if you look hard, you can see the size of a person. Here, there's one, and there's one. So ITER is gigantic. It's aimed to produce 500 megawatts of fusion reactions for about 100 seconds at a time. This is a photograph of ITER's construction. It's halfway through construction. This, of course, is showing you the outside, the bits of the tokamak gradually being put together. And you can get an impression of the size and complexity of it from this picture. Unfortunately, ITER has a rather cumbersome organization because it's a 7-nation collaboration, and it has experienced many delays, and it won't operate in deuterium-tritium and hence be generating fusion reactions until at least the mid-2030s on the present timescale. Ideally, though, what we want is a device that could achieve that burning ignition condition or near to it in a much smaller device, and that looks as though it might be possible. What makes it possible is a breakthrough in technology, which is high-temperature superconducting magnets. So high-temperature superconducting magnets permit a higher magnetic field strength at higher temperatures, and they're more resistant to radiation. And SPARC is the name of a proof-of-principle experiment designed by a group of former MIT students who've banded together to form a company called Commonwealth Fusion Systems, and have also been funded by venture capital rather than by governments. SPARC is about 1/25 of the volume and mass, and hence probably approximately price, of ITER. And it aims to produce a fusion burn in this decade, as opposed to next decade. And last year saw the completion and separate testing of a coil that demonstrates that this new technology of high-temperature superconducting can actually generate a field that can withstand 20 Tesla. And so the device is being constructed at a breakneck pace, because that's what venture capital demands, about 50 miles from MIT. It's arguably the most exciting thing that's happening in fusion energy research today. But the other remarkable development is that there have been a dozen or so privately funded, venture capital funded companies that have sprung up around the world, encouraged by the excitement surrounding Spark, I suspect, and they are aimed at demonstrating fusion energy on a more ambitious timescale than ITER. Many of those companies are actually pursuing stellarators because stellarators have certain advantages. They don't experience some of the technological challenges of tokamaks, even though they have additional challenges of their own, of course. But that's where fusion stands at the moment. I have actually, in my last few years of plasma research, have moved away from this pursuit of fusion energy and begun to take an interest in some of the wider phenomena that go on in plasmas. After all, the scientific enterprise is motivated by the desire to understand and explore the world, looking inward, to understand the composition and microscopic properties of animals, plants, cells, atoms, nuclei, and the fundamental forces, and looking outward to understand our world, to the Earth, to the atmosphere, to the solar system, to the stars, the galaxies, and the entire cosmos. And in these last few years of my scientific career, I've been involved in actually space plasma physics. That came about in part because of my interest in various applications in fusion. But what this phenomenon basically is about is this. The Earth and the Moon are in a space which is actually not a complete vacuum. It's filled with dilute plasma. That dilute plasma is called the solar wind. And I entered into a collaboration with a colleague from Colorado University to discover whether the prediction that I had made, that flow of plasma past solid objects. So in my initial case, it was probes in the edge of tokamaks, but we aren't able to diagnose those sufficiently well to demonstrate whether the theory is right. But in the case of the Moon, we are able to diagnose what's happening in the solar wind wake of the Moon. So this picture illustrates the fact that there is a solar wind flowing past the Moon. There have been satellites orbiting the Moon for many years and making measurements of the electric potential, which is what you need to sense the objects, the solitary waves that are part of our experience and our interest in terms of measurements. And what it shows is that indeed, when you go and analyze the data that's been collected, you find that almost all of the holes that you observe, these solitary waves you observe, are in the wake of the Moon, and that's a very comforting and encouraging sign that the theory is right. By the way, what are solitary waves? This is an example of a solitary wave, not in a plasma. This is a solitary wave on the surface of the River Severn in the United Kingdom that is generated, and it's called a bore. There are other rivers around. But what it is a single wave, and the Severn bore propagates up the River Severn for many miles, preserving its shape. And these are keen surfers trying to take advantage of that wave. That's analogous to the plasma solitary waves that are part of that theory and that set of observations of space plasma. So I'm grateful that I had this opportunity to discover something, to discover something previously unknown about nature. The phenomenon of these electron holes, these solitary waves, has been going on since long before humans walked the Earth. and the marvelous coherence of the natural world inspires in me, as it has inspired in psalmists and scientists for millennia, awe and wonder towards the creation and worship towards its creator. So I want to thank you for allowing me to share that sense of awe with you and to tell you about some of the ways that I and many other scientists have been reaching for the stars. Thank you for your attention. Please do ask me questions. I'll put up the...
Yes, so if you want... Oh, wait.
Yeah.
Yeah.
But if you're here in the room, it's probably easy just to raise your hand and we'll...
Yes, and I can throw this thing because I really want to. Who has questions?
Over there.
Throw. Can you catch?
Yeah, so can you just tell us why this twist is necessary? What would happen if you didn't have the twist? And
What happens if you don't have the twist is that the top of the torus doesn't communicate with the bottom of the torus along the field lines, and the charges very slowly separate, and that causes, that basically compromises the confinement in the torus. So we have to have some way in which the particles can flow along the field lines from the top to the bottom. That's the simplest way I can express it. Can you speak loudly, or do you need a mic? Yeah, where do we get deuterium and the deuterium and tritium from? Deuterium is very abundant on the Earth. 1 part in about 10 to the 4 of all hydrogen atoms on Earth are deuterium, the heavy hydrogen. Tritium is not, because it's radioactive. It has a half-life of about 12 years. And so tritium, when it's formed on Earth, decays away. But we do actually have stores of tritium that are slowly decaying away on the 12-year timescale. And they mostly come, at the moment, from being generated in heavy water-cooled or moderated fission reactors. In the long term, if we had a fusion economy, we would have to generate or replenish the tritium that we burned. And there's a technique why we can do that by breeding it using the neutron that is emitted in the fusion reaction and letting that interact with lithium. If you allow that to happen, then actually the neutron can split lithium and produce 1 or 2 new tritons in the process. So basically, in the long run, for us to have a fusion economy, or even to run permanent fusion reactors, we would have to do, in DT, we would have to do breeding. There are fusion reactions that don't need tritium. I mean, you can react, in principle, deuterium and deuterium, but it's much slower reaction, and consequently, you need to have even better confinement than we are aiming for in DT. So the first fusion reactors, I think, will certainly need to use tritium. Thank you for that question.
We have just an anonymous question.
Okay.
So someone asked, and 6 people liked the question, so 6 people are asking, are you experiencing doubts in your Christian faith, and how do you deal with them, also in light of your growing maturity and understanding?
Okay. Well, I think doubt is part of the way that we all understand the world and improve our understanding. So I'm not dead against doubt. I don't experience doubt because of science. On the contrary, I think there are things in science which inspire me to worship, as I tried to convey in my last closing remarks. I think those people who, those sort of convinced atheists who argue that somehow science has disproved religious faith, and Christianity in particular, simply haven't thought deeply enough about what the whole commitments of science are, and the fact that actually lots of our knowledge is not scientific knowledge. So I would be willing to accept that For example, we can't prove God scientifically, but that doesn't mean that we can't experience God and know something about God. After all, you can't prove the facts of history or the analyses of historians by science, because history is totally different than science. Science is the study of the reproducible way in which the world behaves, whereas history is all about, well, mostly unique events of history. And so its methods of study and gaining knowledge are completely different. And there are many other disciplines, of course, in the university. So while I am committed to science and getting the knowledge that we get through science, I don't at all discount the possibility that there are other ways that we can gain knowledge. And I think that in general, religious knowledge is very much more dependent on historical types of evidence than it is upon scientific evidence. So that's kind of a longish answer to a shortish question. Someone in the audience, yes. Oh,
Can you hear me now?
yes.
Okay, I just have a couple of questions. One thing I want to comment is like, I'm a Christian. I think fusion is almost like Christ. It's coming.
Well, maybe.
I mean,
But we'll come first, right?
Well, yeah, I hope Christ comes first.
Okay, what's your question?
A few questions about, because I am nuclear engineer, retired or unemployed. But in fusion, ever I come to know fusion, actually I tried to get the fusion program when I was a young student in college, but it was shut down, and they say it's about 25 years before.
Well, don't tell me your whole life, just give us a question.
Yes. That's why, I mean, say, fusion is always like about 25 years away, and now it's about 30 years away, they say.
Yeah.
You shows the high temperature coil for the magnetic field coil. I think this is an advancement. So any other technical advancement that you could see that fusion is not just a science research,
Thank
but
you for that question. I get the question. Thank you very much. So I'm going to boil this question down to, when are we actually going to have fusion? Okay, I think that's basically the question. And the answer is, I don't know. People have been asking me this question throughout my entire career, and it's been remarked that we haven't got close enough. I am actually not optimistic that fusion will be on the grid in my lifetime. I don't think it will. And so therefore the question arises, well, if we're worried about climate change, about global warming and so forth, is fusion going to contribute to that? I actually think my own personal opinion is probably not. We need to do things more urgently in terms of reducing our dependence on fossil fuels than fusion will be available. I think in the longer term, fusion is an attractive option. It has certain advantages relative to the other type of nuclear power, which is fission, in terms of safety, in terms of the supply of fuel, and in terms of other aspects of proliferation and so forth, radiation, lower radiation and so forth. But I think for the foreseeable future, we need all the energy sources we have available today for addressing this problem, and we may well need other energy sources in the future. And so I'm not embarrassed about the fact that I spent my career studying fusion, and we still haven't got there. I am disappointed, but I am realistic, I think, about whether we're going to have it immediately. Fusion is an incredibly difficult form of energy, much more difficult than fission.
Okay, one more question from the anonymous speakers. So many believe that one cannot find God in a universitarian environment, so in university. How did you find God then?
How do you find God in a university environment? I actually don't think a university environment is any more difficult than anywhere else. There is, of course, an opinion about most modern universities, they are secular places. It is true that there has been a secular takeover of universities in the last 150 years. Actually, universities were founded largely by people of faith, and in order to teach people how to live according to that faith. We've moved on from that. We live in a secular world, and so yes, I accept the question as a valid question. How did I find the faith? I think there was a whole lot of things. I wasn't a Christian. I wasn't brought up as a Christian. My family weren't Christians. I wasn't ignorant of Christianity. I knew something about the Bible. I'd read the New Testament and so forth, but I didn't believe it. But I had two friends at Cambridge University who were Christians and who were incredibly intelligent people and whose lives I found attractive. That was an important aspect. Another important aspect was that I discovered two new things that I hadn't realized about the Christian faith. One is that the historical evidence for the resurrection of Jesus is extremely good. It's not scientific evidence, it's historical evidence. But you know, in the scale of things for events of that era, it's as well attested as almost anything that people accept in classics and in ancient history. The other thing that came to me as a bit of a surprise, something I hadn't thought about before when I was at university, was the idea that Christ came so that we could have a relationship with God. Not just that God was some, creator out there that set things in motion, but that actually we could have a living relationship with God. And finally, I might mention, I was in a place where I realized that the culture of the university in which I was living was really founded on the Christian faith. And so there was evidence all around me for how influential Christianity had been at building a civilized and thoughtful social order in which I was benefiting. And then eventually I became persuaded that this person, Jesus, really was the Son of God, and I committed my life to following him, and I followed him ever since. And I've experienced blessings through that, and I regard it as something that has been completely formative and has guided my life since then.
Cool. Does anyone have... Okay. Yes, you with the mic.
Thank you. You've alluded to the orders of magnitude improvement, and tokamaks were by far the superior scientific reactors, but they have technological engineering drawbacks for steady-state reactors. So I'm curious if you can say anything about advanced fuel cycles and aneutronic desirability and size, speed, iteration.
Okay.
And who should we look for? Who are the good candidates?
So let me unpack a couple of what's been asked. Aneutronic reactions are fusion reactions which don't give rise to a neutron. They have potential advantage that they would vastly reduce the activation of the materials out of which the reactor was made. And this would be a terrific advantage. The problem with aneutronic reactions is that instead of needing 100 million degrees temperature, you need something more like 1,000 million degrees temperature in order for them to take place at the rate you need to. So people are willing to open their minds and dream big in the fusion business. And there are other aspects of your question which is really about what about alternative concepts? The answer is there are alternative concepts. Some of them are gaining some venture capital funding, some public funding. Most of them, I would say, are concepts which we know won't work. I say we, I mean, obviously the people who are pursuing them don't know that, but those of us who have been in this business for a while consider it a settled fact that they aren't going to work. And that's why I made my remarks about brilliant new ideas. I don't mean to say there are no new ideas. There's enormous amount of very important engineering, as you're well aware, I'm sure, that will need to be done, and we need to be creative about things. So we shouldn't be just dismissive. But I think we also need to take account of the fact that we've been studying fusion for 60 years, and so it's pretty hard to dream up something that's really a serious prospect for being a lot better.
There are 10 people wondering how much energy have we wasted trying to garner the same power as the stars?
Wasted? I don't know if we've wasted. We've used a very modest amount of energy on this research, okay, compared with what we use every day in society, where we use vast quantities of electricity and energy. So if you literally mean energy, in answer to this question, the answer is a negligible amount of energy so far. But of course, maybe you think, maybe you're speaking more metaphorically about energy. You mean how much scientific effort and so forth have we used? Well, I would say I am not at all embarrassed about having spent an enormous amount of my own personal and other people's efforts on this. What we spend on that as a society is tiny in compared to what is spent on weapons development or the exploration of space or even high-energy accelerators. So it's not an embarrassment. We as a society do spend considerable effort in basic science to understand the world, and we should, I think. So that's basically my answer to that question.
Thank you. One more question from the audience, maybe?
Hey, so I wanted to ask, the original idea for fusion came from looking at the stars, and now it's become a really big experimental engineering problem. But would it make sense, similar to how you kind of looked back out to what we see around us, would it make sense also to kind of continue looking into the astronomical aspect of fusion and seeing if we can develop the idea there?
What
like the looking to the stars again for.
Oh, should we look to the stars again? Well, there is a sense in which we are already looking to the stars. After all, solar energy is fusion energy, and so when we have solar panels, we're actually using fusion energy. Of course, that's a trick. That's a rhetorical trick. I don't actually think that anyone believes that we can use gravity on Earth to confine a plasma. And so if we're right that basically in order to get useful energy out of fusion, we have to have temperatures in the ballpark of tens or hundreds of millions of degrees Kelvin, I think we aren't going to be successful in using gravity, and no one really is, as far as I know, even is dreaming it. Okay, so that's sort of my answer to that question, I think.
A few questions from the anonymous poll. So people are wondering about your working environment. So how do you see and experience God in your work? And then during your work, how do you also share your faith with your employees?
Well, I showed you my team. Of course, only a relatively small fraction of those people shares my spiritual commitments. I do think that they respect my spiritual commitments. And when I'm working with people day by day, I think they know I'm a Christian, and from time to time they will ask me about it. There have been students who come to me and wanted to talk about my faith, and there are others in that kind of environment. But I think we as Christians, those of you who are out there who are Christians, understand that we live in a world where we have different views, people live different commitments, and we seek to live well with those people and care for them and enable them to succeed and live a fruitful life regardless of their spiritual commitments. And I think that's a truly Christian viewpoint.
More people from the crowd?
Well,
Okay,
Thanks.
that's an interception.
As a complete novice, we exploit water for hydropower. Could we exploit solar winds?
Good question. What could we do something with the solar wind? Actually, science fiction novels for a long time have supposed that we should use the solar wind for sailing spacecraft. And that it's not so totally stupid. It's not completely impossible. The trouble is that the density of the solar wind is extremely low. It's in the ballpark of 1 or 2 particles per cubic centimeter. So the energy density of the solar wind is very low, and you would have to have gigantic sails in order to kind of gather its energy together. So it's an interesting idea, and science fiction writers have explored it, and scientists have thought about it, but ultimately the power density and the energy density is a bit too low to be making an attractive option. Interesting question.
Another question from the anonymous poll. What is your attitude towards miracles described, for example, in the Bible?
Okay, yeah. I actually I wrote a book whose title is Can a Scientist Believe in Miracles? And this is it. If you want to have a look at it, you are welcome to do so. I urge you, if you've got deep questions about the relationship between science and faith, to read the book. This is the shameless advertising part of the talk. But I want to say the answer to my question, can a scientist believe in miracles, is yes, okay? It's a much longer answer than is easy to give to explain exactly what that means. But I think you have to understand what science is first. You have to understand that science is understanding the way in which the world behaves insofar as it is reproducible. I think you also have to understand what miracles are, and certainly if we take a biblical view of what miracles are extraordinary acts of God. So you have what's the ordinary, the regular reproducible, and you have what's the extraordinary. The methods of science are very poorly able to be applied to the question of miracles. Science can sometimes rule out or explain situations in which there's a charlatan pretending to have miracles, and science can discover that no, that's not really what's going on. But in general, if we have a genuine, unexplained event, extraordinary event, science is not very well, in fact, not able, basically, to decide one way or another whether a miracle has taken place. And so we're in this interesting situation. Those people who assert that science has shown that miracles don't take place haven't really thought deeply about how we go about gaining scientific knowledge. If God, as Christians say, if God is sustaining the world, not just to set it going with some fixed laws, but Christians say God the Son sustains the universe by his word of power, then the laws of nature that we find out are the normal way, the ordinary way in which God sustains the world. And that's something we can have awe towards. But that doesn't prevent God from deciding for his own purposes or for important reasons to allow the universe to behave differently from the way it ordinarily behaves. And that is basically what a miracle is. So to me, the answer to the question is yes, a scientist can believe in miracles. Of course, you should be skeptical about miracles, because if there were miracles happening every instant, then we wouldn't have the reproducible behavior of nature. The fact we have reproducible behavior of nature means the miracles are rare, but it doesn't prove that they never happen.
Could you give an example for such a miracle?
What do you mean by such a miracle?
By a miracle that you were just describing.
Well, I mean, if you think about the Bible, think about Bible miracles. Miracles come in all kinds of different types. There can be situations in which Jesus commanded the storm to stop, okay, while the disciples were threatened on the Sea of Galilee. There's nothing inherently that contradicts what we call the laws of nature about that. It could have just been a coincidence, okay? But it was interpreted by the disciples as a supernatural act of God. And I see no reason why we shouldn't take that view. On the other hand, at the other extreme, you might consider a biblical miracle like the turning of water into wine. Personally, I can't imagine how that could ever take place in a way which was not a violation of the normal behavior of the laws of nature. In other words, it seems to me it's a violation of the laws as we understand them in science. But it was highly well attested. There were lots of people around who saw it took place. So, who am I to say what took place? So there's a whole spectrum of different types of things that religious believers take to be the acts of God. And all of those require some level of interpretation in order to see God at work. At least one needs an openness to the possibility that God might act in extraordinary ways. Thank you for that question.
We have a question here.
Yeah. So if we have research about stellarators and research about tokamaks, and stellarators have the advantage that you don't have to reset a current, and they can run for longer, and their main disadvantage is that you need experts to install them, or one of the main disadvantages, then why did the ITER Commission still decide to build a tokamak when the only thing they weren't lacking was experts?
Well, no, it wasn't to do with experts. I might have misled you in that respect. It was to do with our knowledge. Our knowledge has improved of accelerators since ITER was embarked upon. But it's still the case, and I showed you this on the graph, it's still the case that they don't perform as spectacularly as tokamaks. And the idea of ITER was to move as fast as we could towards reaching the burning plasma regime, preferably ignited, but at least in the burning plasma regime where the self-heating of the plasma was large, in order, in part, to make sure that nothing drastic happens when we reach that point. So that was the motivation. And stellarators are still, well, certainly weren't in the 2000s and are still actually not in the position where we could easily propose an experiment to do that. So the bottom line is, I think it's reasonable to keep some of one's options open. But of course, you can't keep all of your options open if you're going to commit to a big project. And so you have to make some kind of judgment call on what should we do about it. And so I would argue that it was a reasonable judgment to say we would build a big tokamak because that was by far the most likely to succeed and the most feasible to build. Yeah.
Did you ever experience like discrimination or some kind of disadvantages in your career because of your face?
Okay. Yeah. I don't consider that I've ever substantially at MIT been discriminated against because I'm an outspoken Christian. Maybe there are some quote-unquote disadvantages. I think most of them are advantages, but for example, I don't work basically more than 6 days a week because I think that's one of the principles on which Christianity teaches a good life should be lived. And that's a way of having a balanced life in which, your family, your kids, and so forth are important. I mean, there are people, who work 80 hours a week sort of on a permanent basis. Maybe that's a disadvantage to me. I don't know. I'm not sure that it is, actually, because I'm not sure that people who work those long weeks are really as creative as people who take rests and breaks and so forth. But maybe it's the case. It might be the case that I've been discriminated against behind my back and I haven't realized it. I know there are people at MIT faculty members at MIT who on occasions have criticized my ethical viewpoints, which are Christian, and basically, badmouth me, but never to my face. Never to my face. I don't think anyone ever would. People have asked me challenging questions. How can you, as a scientist, believe all of that? That sort of question. But that I don't regard that as a disadvantage. I regard that as a potentially an interesting question to spend some time talking to somebody.
Yeah, so that brings me to the question, what are your thoughts about this conflict between science and faith? One big conflict, for example, is how the earth was created and how old it is. 6,000 years versus millions.
Well, I don't think there's much remaining conflict about those things. I don't think Christians these days have any problem recognizing that the earth orbits the sun rather than the sun orbiting the earth. Now, of course, there were historically some arguments about this, and Galileo got it in the neck for advocating, the Copernican system. Actually, he probably deserved it because he wrote a very rude book in which he portrayed the Pope and the views of the Pope as in the mouths of Simplicius, in other words, the simpleton. And so he said lots of rude things about the people who disagreed with him. He was a cantankerous and very self-opinionated character, a very brilliant scientist, and by the way, a deeply committed Christian until to the end of his life, okay? So there are arguments to be had as our understanding of the world develops. And it's not unreasonable to have those arguments. Sometimes they become rather, troubled arguments. As far as the age of the earth is concerned, I know, of course, there are people who interpret the first few chapters of Genesis in a very literalistic way. I just think that's bad Bible interpretation. I think the first few chapters of Genesis are not designed to teach us how God created the earth. They're designed to teach us that God created the earth. And they were actually designed for that purpose for the Hebrews initially, because the Hebrews were in this situation where they were a tribe amongst many other tribes, and each tribe had their tribal deities, their tribal gods. And the whole point of Genesis was to make clear to the Hebrews that if God is God, then he is the God of everything. And not simply a tribal deity, but that he's actually the creator of the entire universe. And so that particular aspect of interpretation is just, I think, misguided. And by the way, the great Christian teachers of antiquity, the fathers, a large number, there were people who took the early chapters of Genesis literally, but there were more of them who actually took it as being figurative. And St. Augustine, in the 5th century, wrote a whole book which was a book called the Literal Interpretation of Genesis, and his main purpose was to advocate against a literal interpretation of Genesis. So this view of the Bible has a very long Christian tradition. And so, as far as I'm concerned, I don't have any problem in regarding the universe as 13.8 billion years old, and the Earth as being 4 billion or whatever it is, and so forth. So I just don't see that conflict, even though it exists in some parts of Christian interpretation. Thank you.
Thank you. Do we have any more questions? Yeah.
My question is, which scientific findings mind-boggle you most, and just awe you most with regards to God's creation?
Well, okay. I think I'd be very hard-pressed to select any one. And I think actually the things that exist within creation that I think point to there being an intelligent creator are not specific, results. They're not specific difficulties. So, for example, there's a whole long history of arguing about there are things in the world which could not have happened unless God had created them. I am not particularly attracted to those kinds of ideas. I am much more comfortable with avoiding a view that is sometimes called the God of the gaps, that somehow we can detect God's presence by looking at things that had to have God doing them. I'm much more interested in understanding the coherence and appreciating the coherence of the creation. And so that makes it basically be your question being something that I'm going to sidestep, because I don't think there's one thing. I think it's the whole picture. And C.S. Lewis, who's a famous Christian writer, once wrote about about one aspect of this sort of generic understanding of the world and the way that draws us to think about the Creator. And he said he said it by analogy that let's see. It's to do with. I'm going to be unable to do the exact quote, but the idea is generally that it's not so much that the Christian faith itself is the thing which I want to focus on. It's that the light that we see illuminates the whole world. And so I think that the Christian faith makes sense of the broad picture of life and the universe and everything, if you like, rather than it makes sense of individual particular things. Sorry, I lost my quote, but I'm sure some of you out there know the quote that I was grasping for. There was another person here, yes.
Yeah. So my question is about fusion reactors again.
Yeah.
So you mentioned towards the end of your talk that smaller reactors are pursued again nowadays. And so I was wondering what are the challenges and the opportunities with those, and whether or not that's the way forward to make progress.
Well, we'd like a fusion reactor to be as small as possible. The problem is that we don't know how to make it's harder to make, let's say, a smaller reactor have enough confinement to produce a fusion reactor. That's different from the fission reactors. You may also have heard about modular, compact fission reactors, which are actually very topical these days in nuclear energy. And the problem in fusion is that it's very hard to make a small reactor. One of the reasons is because the penetration of neutrons is about 1 meter or 2 through solid materials. So if you're running DT fusion, you're going to have a reactor that has at least the size of, be about this big, at least, okay? Because otherwise you're not going to be able to collect all the neutrons that are being emitted and take their energy and use it to generate electricity. So, but of course, this isn't the size of ITER. ITER is the size of this room, okay? So in order to reduce the cost, we would like to make it smaller. So how small can we make it? The basic answer is it depends how strong a magnetic field you can generate. If you can generate a very strong magnetic field, the size of the helix that the particles generate is inversely proportional to the strength of the magnetic field. So if you strengthen the magnetic field, you improve the confinement. And so basically the answer is depends on how much magnetic field you can have. That isn't a complete answer to your question, but basically we want to reduce the cost and make it something we can build in a compact size, but not in the back of a DeLorean. Okay.
Thank you. Unfortunately, that's all time we have left for questions, but you can meet Professor Hutchinson afterwards at the apéro if you have any other questions. Yeah, that brings us to the end. Thank you so much for the knowledge that you shared with us and your thoughts. We have something small for you just to say thank you. And we can give him a round of applause. So just if you can take a moment and if you have something to say in terms of feedback, it would be nice if you can scan the code and maybe leave a comment what you would like to see next time, or if you have any recommendations, it would be greatly appreciated. Yeah, so thank you to VBG, who's also the organizer of these talks every Tuesday. It's a Christian student association from the university, and we talk about faith and science and how it collaborates, and it was really, really cool to have you here and share your wisdom with us. So thank you for that. Yeah, then, sorry. I would like to invite all of you also. There's an event that's held by VBG. It's the Gartenfest, and it's on Friday in the Aki Garden. It starts at 7, and everyone is welcome. If you want more information, you can scan the QR code again. And then there's also just two associations that I want to inform you about. It's Campus Live. It's similar to VBG. They meet regularly in small groups, and they have community nights once a month. If you want more information, scan the code. And then there's also a dossier and forum, and it's for Christian professors. So if you want to talk to a professor, you can have a look here. And some of the next events, as I said, the Gartenfest this Friday, and then every Tuesday the VBG meets and talk about interesting topics. So have a look at future events, and it would be really cool to see some of you there. So thank you so much, and I hope to see you at the apéro after. Thank you. Have a good evening.